Hello, wonderful people. Welcome to Cosmology Talks. Today we have the first cosmological results from the Dark Energy Spectroscopic Instrument, or Desi, the year one data release. Specifically today, results from BAO. So excitement would be an understatement. Presenting the results, we have Seshadri Nadathur, who is an Ernest Rutherford Fellow at the University of Portsmouth, and Andreu Font-Ribera, who is a staff scientist at IFE in Barcelona. This is a results talk about an experiment cosmology has been waiting on for a while, so I'm not going to hold the stage for any longer. Andreu, Sesh, do you want to start by telling us very briefly about Desi, why it's special, and what the collaboration has done? And then in a minute or two, we'll see the results.
We're very happy to be here to present the first results from the Dark Energy Spectroscopic Instrument, Desi. So this is a multi-object spectrograph that we have installed at the 4-meter Mayal telescope at Kitt Peak Observatory in Arizona in the US. And during 5 years, Desi will observe 40 million galaxies and quasar redshifts. So we already started 3 years ago, and today we will be presenting the results from the first year of data. One of our main measurements is the measurements of Baryon Acoustic Oscillations, and that allows us to time the expansion of the universe across redshifts and use that to understand the nature of dark energy better.
Awesome. Okay, no more waiting. Let's see the cosmological results themselves. And just a quick warning to the viewer, there will be bits here we don't necessarily understand. I wanted Sesh and Andreu to show us the results right away, so we don't have to wait till the end of the video. So what we'll do is have a quick peek now and find out what Andreu and Sesh find interesting, noteworthy, or peculiar about the results. And then we'll take a step back and they can give us all the background and all the details to fully flesh out exactly why it is that it is these results and why these things are noteworthy. And then we'll come back to the results near the end and re-examine these noteworthy bits.
So we have prepared 2 slides to tease you. The first one is the measurements of BAO across different redshifts using different tracers from left to right, using bright galaxies, using luminous red galaxies, emission line galaxies, quasars, and then the Lyman alpha forest that allows us to go farther back in time, 11 billion years ago. So these 7 BAO measurements, as you can see in this slide, they are broadly consistent with the prediction from a flat lambda CDM universe. But there are some hints that maybe the equation state of dark energy is not just -1, as in the cosmological constant, but maybe a little more exotic and a little more exciting. So you can see that in the next slide, where we show the constraints on the 2 parameters parameterizing this equation of state as a function of time, W0 and WA. And here we present the results from Desi BAO combined with CMB information from Planck 2018 and the ACT DR6 lensing, and then in combination with 3 different types of supernovae compilation, Pantheon Plus, Union 3, and DS Year 5. So you can see that those different constraints are broadly consistent with each other, and that all of them hint to deviations from what lambda CDM would expect. That's the blue cross that you see in the top left.
2 things that I'd like you to touch on now, and you can just state things now without argument or justification. I just want you to state them, so long as you then are actually sort of going to explain it in detail as the talk goes on. How much of this result that's on the screen right now is in the actual physics itself and is not potentially just a tension between BAO and supernovae? Would Desi BAO on their own favor this less than 0, greater than -1 region, or is this somehow a tension between the data sets?
That is a really good question. So Desi BAO by itself favors W0 of greater than -1 and WA of less than 0, but it doesn't have the statistical significance to rule out lambda CDM at any great precision. I will talk about Desi alone. Desi plus CMB slightly rules out lambda CDM, but not great statistical significance. Desi plus any of these supernova datasets again favors the same sort of region of parameter space, but without the full statistical significance. And then when you put all 3 of them together, then you get the higher statistical significance that we're showing in this plot.
And this plot, if one was to overlay SDSS results, is not in tension with them. They just had sufficiently large error bars that this was totally allowed by them?
Yes. The change in the error bars is not massive between SDSS and Desi in this particular model, but the central values do shift a little bit, so that the central value still favors the same region of this same quadrant in the plot, but lambda CDM would be ruled out with somewhat lower significance if I used SDSS.
Cool. And I'm guessing from your silence about everything else that more or less the other cosmological stuff you've measured is in line with lambda CDM and expectations then.
Dark energy not being a cosmological constant is potentially the biggest news. There's various other little things that are firstly not as significant and secondly not as groundbreaking as a time evolving dark energy equation of state.
We have sharpened quite a bit the neutrino mass bounds, but we haven't yet detected that.
What I found interesting about your neutrino mass result is that you're almost reaching the lower bound from particle physics. And at some point, if cosmology crosses that lower bound without a detection, there'll be a lot of raised eyebrows in fundamental physics.
Right. So we're going to be talking about this later, but talking about priors so early in the talk would be confusing, and talking without mentioning priors maybe a little bit misleading.
From a cosmology side, we've measured the Hubble constant, so we have something to say about the Hubble tension. You can't measure the Hubble constant with Desi BAO alone, so measurements that we get are from combining Desi BAO with some external datasets or external priors, Big Bang nucleosynthesis, and the acoustic angular scale, the CMB, or directly with the CMB itself. We'll mention that the Hubble value is slightly larger than Planck, which is kind of interesting, but it's still perfectly consistent with Planck and discrepant with local distance ladder measurements from shoes, for instance. We've got a lot of results in the paper for various other things like constraints on curvature or constraints on the dark energy equation of state W if it were a constant, which is probably, it's a bit of a toy model, so it's not that realistic. But some of those things I've left out of the slides for this talk just because of constraints of time. And the paper is over 40 pages long, and it's one of 3 flagship papers that are coming out here. So I felt like we should focus on the highlights.
So we're going to be, first of all, thanking our funding institutions, funding agencies, and the 72 participating institutions in Desi. We started more than 10 years ago, and we are now presenting the results from the first year. I will start with introduction to BAO and Desi, then Sesh will continue presenting the results of BAO measurements from galaxies and quasars. I will follow with the results using the Lyman alpha forest at higher redshift, and then finally Sesh will present the cosmological constraints from Desi BAO. Baryon Acoustic Oscillations, BAO, is one of the 2 ways that we have to measure the distance redshift relation. I mean, there are more than 2, but those 2 are probably the most promising ones. And why is it important to measure this distance redshift relation is because, it allows us to study better the dark energy and to try to understand better its nature. So we want to time the expansion at different cosmic times, and that's what we are doing with this standard ruler. So what is this ruler? So we have this magic ruler coming from a competition between gravity and pressure in the early universe, in the primordial plasma. And you can see in this animation, initial overdensities created this acoustic wave. And at redshift of 1,000 or so, photons decoupled from the baryons because hydrogen atoms are formed for the first time. And at that point, the sound waves stop. And we are left with a particular scale that is imprinted in the distribution of matter. This scale corresponds to the sound horizon, to how much these waves traveled, and it corresponds to roughly 150 megaparsecs. So this is our magic ruler that we're going to be using to time the expansion of the universe across cosmic time. So the next step is to use a telescope, observe millions of galaxies at different redshifts, and measure the correlations in the angular directions as a function of angle, and try to detect in those correlations a particular scale that has this extra correlation coming from these acoustic waves. And once you detect that, you can interpret that as a measurement of the ratio from the sun horizon, or RD, divided by the distance to that redshift, or DM. If you measure BAO also along the line of sight, you see this correlation as a function of redshift separation, and you see a particular redshift separation that has an extra correlation, and that again corresponds to that acoustic scale. And we can interpret that as a product of the sun horizon times the Hubble expansion at that redshift. So from the same group of galaxies, we obtain 2 measurements, a measurement of the angular diameter distance to that redshift and a measurement of the Hubble expansion at that particular redshift.
Is it worth emphasizing that this figure you've got on the left is an over-exaggerated version of this?
It's an artist's impression.
Exactly. In the reality, it's a very subtle extra correlation of around 5 or 10% extra correlation at 150 megaparsecs. From every set of galaxies, we measure BAO along the line of sight and in the transverse direction, and that allows us to measure both measurements of the Hubble expansion at the time and the angular diameter distance to those galaxies. So then we put all of those together, these 7 different measurements of BAO at different redshifts, and that's what allows us to constrain cosmological models, and in particular to study the nature of dark energy. So let's move to the description of Desi. So we're going to start by describing the instrument. And I often try to use this video because it makes a much better job at describing the instrument that I could do.
Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure Desi maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in Desi's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows Desi to target sequences of thousands of galaxies at a time. The optical fibers, which serve as Desi's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs.
Then we use these spectrographs to get very accurate spectra of these objects, and we obtain redshifts for the different galaxies and quasars in the data set. So now that I've described the instrument, let's move to the Desi survey. So this is a 5-year campaign that started 3 years ago in May 2021. And during these 5 years, Desi will observe 40 million redshifts using different tracers. So at low redshift, closer to us, we have 13 million bright galaxies, and we observe some of those during the bright time, meaning when the moon is up in the sky and it's a little bit harder to look very distant objects, we look at nearby galaxies. We also observe about 8 million luminous red galaxies, and that allows us to go to redshift 1. We can go to higher redshift using emission line galaxies. Those are younger type of galaxies, and we'll observe 16 million of those. We detect a very clear emission line thanks to our spectrographs. Then the same redshift range is also covered by quasars, but we also can use quasars above redshift 2 to study the Lyman alpha forest. I'm going to be talking about the Lyman alpha forest a bit later in the talk. So using this very wide range of redshift, we can constrain dark energy through 7 BAO measurements. So here you can see the footprint of the first year of Desi data observations. In particular, this is a footprint for the dark time. As I mentioned, during the bright time, we also observe low redshift galaxies. And what you can see here is that we have 2 different patches of the sky that we observe, what we call the North Galactic Cap and the South Galactic Cap. And you can also see here is that the North Galactic Cap has some areas covered in blue, some areas covered in red. So Desi will be doing different passes on the same part of the sky. So if it has only been observed once, they look blue. If we have observed already up to 4 times a particular area, it will look dark red. So the year 1 data set is a little bit patchy. So you can see that some of the results will be already really good, but it will be much better once you have the year 3 and the final Desi data sets. So at the bottom of this slide, you can see the timeline. We had first light in 2019. While we were working on survey validation, COVID happened, so we had to pause for a while, but we were able to restart, and we started the main survey in May 2021. So in June 2022, that's the end of the first year of observations. But in today, so this week, is important for 2 reasons. One reason is that we are releasing the first cosmological results, and that's what we are presenting today. But also this week marks the end of the year 3 data acquisition. So we all the data that we obtain until today will be considered part of the data release 3 that will be discussed in a couple of years from now, I guess.
Data release 2.
Absolutely
Year
right.
3,
Sorry, yes,
data release 2.
Yes.
Why, when you have this pipeline that you've now got, that you can take 1 year of data and turn it into cosmology results, why can you not just like copy and paste to year 2 and year 3? It's the same telescope looking at the same sky, different parts of the sky maybe, but the same sky.
I think the short answer is that the more data you have, the smaller the error bars, and therefore also the more stringent your requirements on terms of systematics and things like this. So, for BAO, you could imagine that we could be able to provide a version of the year 3 analysis that would be pretty close to the final one in a matter of months. But, to cross all the boxes, to do all the blind tests, to do all the data splits and robustness and all these things, those takes a lot of time. So every time you have a new data set, you need to go again through all of those. And, the larger the data set, the more complicated it is to pass all those tests. Then there's another technical problem that is, for some of these studies, you need to have a very realistic set of synthetic data, because you need those for the covariance matrices. And we can only get those when we have finished taking data, because we don't know which areas we will cover, with which completeness, et cetera, et cetera. So once we have the final data set, then we generate those synthetic data sets, and then we can compute the covariances and so on. So it takes a few months, if not a year.
So two little things to add to that. There's just a little bit more color. The first thing is the data acquisition has finished this week, but the data systems team don't actually provide us with the final sort of fully vetted catalogs for another few months, possibly up to 6 months. So they run new processing on that set of data. It's just that they've decided that data beyond March the 28th or something is not going to be included in the year 3 sample anymore. So there's that kind of delay. The other thing is that, as Andreu was hinting, there are analyses that are at different levels of readiness. So where some of them we can almost press play and just repeat it, like the BAO analysis, and others where even the DR1 analyses are not yet complete. We haven't released those results. And the DR3 ones are going to be significantly more complicated and require a lot more work. But given the sort of tantalizing hints of interesting dark energy physics, and therefore the need to try to provide more data to address these questions as soon as possible, it is potentially the case that we split off the easier analyses and do those quicker, and then the more complex analyses will progress at the pace that they progress.
I guess also, if in your year 1 results you are seeing hints of genuine new physics, you want to then take a step back for the year 2 and 3 results and say, let's just be ultra careful. We if we have made a mistake in year 1 and it's not just a statistical fluctuation or new physics, let's make sure we don't double down on our mistake.
I don't think our message is that we've made a mistake in year 1.
Yeah.
We're pretty confident about the BAO.
So in this slide, you also see the data release 1 from a different point of view. So here we are showing redshift distributions of the different tracers. In particular, in the left, we're showing the number density of the different galaxy tracers. And on the right, you can show the distribution of the quasars that we use for Lyman alpha forest observations above redshift 2. And in both cases, it's at least a factor of 2, if not 3 times larger than what the Sloan Digital Sky Survey obtained during the BOSS and eBOSS projects. So today on the archive, actually tomorrow on the archive, today on the Desi website, you can see 3 of these first cosmological analyses from DR1. They are highlighted in blue. There are other analyses that will be reported in a few months, and those are the ones that use the full shape of galaxy clustering and its cosmological interpretation. So today we're going to be talking only about the BAO measurements and the cosmological constraint from BAO measurements. And I'm naming here on the right the co-leads of these 3 different, what we call key projects in Desi. There will be also 15 companion papers that you can see today on the website that describe some of the more technical details of this analysis. So I leave it now to Sesh to talk about the BAO measurements from galaxies and quasars.
This is somewhat of a general introduction to BAO, so some of these things will be reflected in Andreu's talk as well. But I just wanted to start off by introducing the scaling parameters and what we're actually going to be measuring with the BAO. So as Andreu talked about in the first few slides, BAO is a standard ruler, and we can measure this standard ruler perpendicular to the line of sight, so the angular size of it, and we can also measure it parallel to the line of sight. And we define these 2 scaling parameters, alpha perpendicular and alpha parallel, which are dimensionless quantities, giving you the ratio of dm over rd or dh over rd to their values in some chosen fiducial cosmology. And so, if these alpha scaling parameters differ from 1, then the true universe cosmology is going to be different from the one that we've assumed in our fiducial model. And I just put 2 little sort of mnemonic images on the side to indicate stretching of the BAO perpendicular to the line of sight or along the line of sight. And these things are going to recur on later slides just to help you keep in mind what we're measuring.
At this point, though, when you say different to the fiducial cosmology, you could be talking about within lambda CDM just...
Yeah, absolutely. So within lambda CDM, you could have different values of the cosmological parameters, in particular omega matter. and that could give you differences in these scaling parameters. Or it could be something more complicated, so you move away from the flat lambda CDM model paradigm totally, and you have dark energy or spatial curvature or something like that, and that can also be captured in these.
And there's one of the supporting papers that I mentioned shows that it doesn't really matter a lot which fiducial cosmology you choose. You can choose different types of fiducial cosmologies, and as long as they are not really far from the truth, you do recover the right cosmology. So.
Yeah. With these scaling parameters, one of the other things that we do is we change the basis of parameterization. So quite often I'll have scaling parameters like this, alpha perpendicular and alpha parallel, but we can also decompose it differently into parameters that alpha iso, which determines the overall isotropic size of the standard ruler, and an Alcock-Pyczynski parameter alpha AP, which is telling you about the anisotropy of that ruler. So these are perfectly equivalent reparameterizations. And in fact, in Lyman alpha forest, they don't use alpha iso, they use a slightly different reparameterization, but it's basically, we're still looking at the overall size of the ruler and the anisotropy. And just one final thing is, sometimes in some of the redshift bins, we don't quite have the requisite signal to noise ratio at the moment. So in order to be able to measure both scaling parameters simultaneously. So when that happens, we just measure alpha iso, just the overall size of the BAO. So those are the different parameterizations of the scaling parameters that I'll be referring to later on. One thing I just wanted to highlight is that the BAO standard ruler is affected by nonlinear gravitational evolution with time. So this image is just showing you, starting off with a peak in the correlation that is very nice and symmetrical at very early times, but then as structures evolve, structures grow, and peculiar velocities move things around, that ruler gets a bit blurred and also shrinks a bit. And this would naturally affect the accuracy and precision with which we can do the standard ruler test. So one of the important things that we do for galaxy BAO, or galaxy and quasar BAO, is that we use a density field reconstruction technique. And this is basically estimating the displacement field that happens from this gravitational evolution and undoing it. And this is a technique that's been around for 15 years. And what it does is it manages to put the galaxy positions back to where they would have been, and by doing so improves the precision and accuracy with which you can actually measure the BAO. This next slide is just to give you some examples of how this works. So what I've done is, on the left-hand side, I'm showing you that BAO peak in the correlation function. So this is in configuration space, and you can see it as a single peak. On the right-hand side, it's in Fourier space, so that peak becomes a series of wiggles. And in both plots, the gray points show you what the BAO would look like without using the reconstruction, and then the colored ones are what we get with reconstruction. This is taken from a series of several mock data sets, so it's more precise than we would actually get from the Desi data, but that helps because it highlights the improvement a bit more clearly. And these are two example data sets from what we use in the real Desi data. Also, the examples I've chosen for these plots are deliberately chosen for as cases where reconstruction works really well. Depending on the shot noise of the sample and so on, reconstruction might not actually provide too much of an improvement. Then we have the question of what's different with the Desi BAO analysis, because we've been doing BAO analyses for decades, really. So I just wanted to go through a couple of important things about Desi. And the first one is obviously just the data. It's already the biggest ever BAO dataset. Whether you measure that in terms of the number of redshifts, or you measure it in terms of the effective volume. And so this is just a repeat of a plot we've shown before, showing the redshift distribution of our traces. We've got 5.7 million unique extragalactic redshifts between redshift of 0.1 and redshift of 2.1 for all of these galaxy and quasar samples. The effective cosmic volume is about 18 gigaparsec cubed. In terms of the number of traces alone, we've got a factor of about 3 more than SDSS had over the full 2 decades of their observations. And this is just in 1 year of Desi. So this is an amazing data set to be using, and it's only going to get better.
And what is the volume of a factor of 3 bigger?
No, the volume isn't a factor of 3 bigger, and that's because the effective volume it depends on the bias of the tracers, and so actually an individual LRG counts for more than an emission line galaxy, or and we observe a lot more emission line galaxies than SDSS did, but not quite as many more LRGs. And in fact, at the lowest redshifts, our effective volume is still slightly smaller than SDSS was, but we will surpass SDSS as time goes by.
I think you're going to have to unpack for me what effective cosmic volume means now, because I was assuming when you said volume, you literally just meant if I put a box around all the galaxies.
Yeah, no, it's not just that. So you've got to weight it by basically by the sort of the power in your signal detection. So it goes with the amplitude of the power spectrum that you would measure.
It's basically a way of parameterizing how well you're going to measure BAO.
Another thing to highlight is that we've done this analysis in a blind way in order to mitigate against any possible observer bias or confirmation bias or something. And what's actually quite interesting about this is that we've implemented this blinding at the catalog level, which I think is possibly the first time that it's been done, certainly for a spectroscopic BAO measurement, but maybe for any kind of a BAO measurement, to have this catalog level blinding, which is more complicated, but also more robust or more secure. And so the way that this works is, for each galaxy that we've measured, we have an RA, a DEC, and a redshift measured on the sky. And then you need to assume a fiducial cosmology model to convert those angular and redshift positions to Cartesian XYZ coordinates. And we do that, and then we take a different blinded cosmology that has some dark energy equation of state and some different value of omega matter that we don't know, and convert that back into some new redshift position. So RA and DEC remain the same, but you get a new blinded redshift for each galaxy. And then it's the blinded redshifts that are in the catalogs that are provided for analysis until everything is secure, and then we can press a button and unblind and have the true catalogs. The blinding also includes other features, so that there's an extra step to the blinding that changes the peculiar velocity contributions to blind us against growth rate measurements, but we're not talking about growth rate in this talk. And there's also a weight space blinding method to blind us against FNL, primordial non-Gaussianity. Again, that's a subject of a different talk later on.
When you have this RA DEC Z goes to XYZ, peculiar velocity also affects that, right? Like there's not a one-to-one correspondence between little z and distance from us.
There is a one-to-one correspondence between little z and the Cartesian coordinates, because that is literally me just assuming, that the redshift is the Hubble flow, which is what you do when you assume when you put in a fiducial cosmology. What you would get, peculiar velocity contributions mean that the XYZ Cartesian coordinates you obtain from doing this are in redshift space. So they have particular distortions in the pattern of galaxies in Cartesian coordinates. Those aren't particularly relevant for BAO. That's why I didn't go into details about that.
How come these other analyses aren't panicking that they've been unblinded?
Because the different analyses run on different timescales. So the other analyses now have to just not look at the unblinded data catalogs and only look at the original blinded ones. Okay, so there's the blinding analysis, which is an important new step. There's also a number of other things. There's new theory developments in how we should do the BAO fitting, and that's in this paper by Stephen Chen, Cullen Howlett et al. That came out a little bit earlier this year. It's a very good paper. I do recommend people read it. It's very thorough. I really enjoyed reading it a lot. And beyond those, which I don't really have time, unfortunately, to cover those theory developments, we also have new and improved reconstruction methods and codes. And then perhaps the most important thing is that the method we apply to the entire pipeline to measure BAO and to obtain our fits and so on is done in a unified way for all the discrete galaxy and quasar tracers. Lyman alpha is a little bit different. Andreu will talk about that later. But at least for all the galaxies and the quasars, do everything in the same way. And we have a whole set of tests for systematic errors. We do all those tests before unblinding so that we set our systematic error budget before we have a look at the real data. And finally, there's a combined tracer method, which we use in this Redshift bin, where we have both LRGs and ELGs overlapping. And that's a new thing that hasn't been done before. I don't have time to go into the details of all of those things, but I just wanted to briefly mention some of the types of things that we're testing for when we look at these possible sources of systematic errors. So there's observational effects in the data. For Desi, one of the important ones is the fiber assignment, which galaxies actually receive a fiber and get their redshift measured. Not all of them do. There's also the imaging that we use in order to select targets and so on. There's the reconstruction algorithm and how exactly we apply that. There's the choice of the covariance matrix and how we construct that. There's possible shortfalls in the theory modeling, even though I said it was great. Potentially things might not match exactly. There's the choice of the fiducial cosmology that we alluded to earlier. And then we test all of these things on mocks, and in these mocks we have to populate dark matter halos with galaxies according to some sort of prescription, and there's uncertainties in exactly how that galaxy halo connection is made. So potentially that might be a source of systematic error. So we test all of these things, and the summary is that the first three of them don't have any effect at all that we could detect. So it doesn't affect the BAO error. And for the last three, we are able to, using many mocks, make a statistically significant detection of some small systematic, but that systematic error is much smaller than the statistical uncertainties from the actual Desi data. And so the maximum effect is that the total error on the BAO measurement becomes 5% larger than it would be just from statistical errors alone. So the systematic errors are totally subdominant for all of these measurements. And just because it's nice to have a figure, I put one figure which shows tests on the blinded data of different types of different choices of analysis, different cuts on the data, different priors and different reconstruction methods and so on, and how they shift or don't shift the recovered BAO measurement. So these are all very consistent, which is why we're confident that the systematic errors are really small.
And I suppose that previous slide reinforces a point Andrea made in response to my question of why not just do the analysis for the year 3 data, is that I guess for the year 3 data, the claim that the systematic errors are much, much smaller than the statistical ones will become weaker, and therefore you have to control for them more.
Yeah, that's right. And the precision with which we can detect any possible systematic errors is really limited by the number of accurate mocks that we have to run these analyses on. And building more mocks takes a lot of time, both real time and computing time.
If you did want to, just for 60 seconds, talk about the new theory developments from Chin and Howlett, what would you say?
Something that maybe could be said is that in SDSS, when we presented the results, basically there were measurements in configuration space, measurements in Fourier space. Each of them used slightly different implementations of the methodology, and each tracer had different choices. So in this sense, now we have a model that we can apply consistently to both configuration space and Fourier space. I think this is one of the things I like most.
Yeah. So one of the things that Stephen and Cullen are particularly proud of is also that the modeling is all done in Fourier space, but it's self-consistently converted into configuration space for when we want to fit the correlation function measurements in configuration space. Whereas previously, Fourier space and configuration space was sort of treated slightly differently in the theory modeling. In SDSS, it didn't actually have a big effect that you did it in this slightly inconsistent way, but it's really nice now that we have a fully self-consistent treatment of the model. Right, so having given you the background of the tests and so on, here's the actual blinded data results. And what I'm going to do is I'm just going to first show you some really pretty plots. So here's two examples. These configuration space measurements of the BAO peak. Top panel is the monopole. Bottom panel is the quadrupole, so they're measuring the overall scale and the anisotropy. I've chosen almost at random two different redshift bins and tracers. The one on the left is the combined LRG plus ELG sample. So that's actually the first time that a combined tracer's been used. The one on the right is emission line galaxies by themselves. And it's the first time that we've got a really nice, precise BAO measurement from emission line galaxies. Emission line galaxies were used in EBOS, but the measurement wasn't very precise. And then just because the plots are so pretty, let me show you this in Fourier space. And I've chosen two different tracers just as an example here. And you can see pre-reconstruction and post-reconstruction measurements. And those BAO wiggles are really clear.
Do you mind just quickly explaining why there is this anisotropy signal? Because I think explaining why there is a BAO was done totally well in the intro.
Oh, right. Okay. So the anisotropy signal links back to the question that you asked earlier about the peculiar velocity distortions that exist in the data. And so if we could measure the redshifts without the peculiar velocity contribution, the Doppler contribution to that redshift, then we wouldn't have any anisotropy. Everything would be perfectly isotropic. So we'd have this BAO peak in the monopole, and the quadrupole would have zero signal. But there are peculiar velocities, and so we do see an anisotropy in the signal, and we can model that. And so that is basically telling us that if the true universe cosmology is exactly equal to the fiducial cosmology, we still expect an anisotropic contribution from these peculiar velocities. In case the true universe cosmology isn't the same as the fiducial cosmology, then we'd be introducing some anisotropy of our own just because we've used the wrong model to convert redshifts to distances. And so we want to be able to simultaneously model both of those effects and correct for them. That's why the quadrupole is giving you a measurement of the anisotropy of the ruler after you marginalize over any redshift space distortion effects. So these plots are just to show you what the actual data looks like, and they're very pretty plots, so put them in. But really what people are most interested in is what does this tell us for cosmology. So this is the cosmology plot, as it were. So it's plotting in slightly confusing units because I've put in an unnecessary redshift scaling just to make the plot look nice. But this is showing you essentially the distance scale measurements on the left-hand side. So it's a measure of the overall, it's coming from the overall size of the BAO for all of the different discrete tracers versus what the Planck lambda CDM model would predict, plus or minus 1 sigma errors, and also the best fit lambda CDM model as a separate solid gray line.
Best fit to the Desi data, you mean?
Yeah, best fit to the Desi data, that's right. And on the right-hand side is a measure of the anisotropy. So it's a ratio of the transverse co-moving distance to the Hubble distance, and again with a redshift scaling just to make the plot look nice. And that's coming from the anisotropic measurements. And you'll notice that there are more data points on the left than on the right, and that's because, as I said, in some redshift bins we don't quite have the signal-to-noise ratio to measure both of these quantities simultaneously, so we only measure the overall scale.
Should I already know the difference between yellow LRG and orange LRG? Or
yellow LRG is just LRGs at a slightly lower redshift bin. So the yellow one is between redshift 0.4 and 0.6. Red is between 0.6 and 0.8. And then there's another LRG bin between 0.8 and 1.1 in redshift. And that's combined with the ELGs in that same redshift bin in this plot, and so shown in purple.
And that yellow data point is not something to get worried about?
I mean, it is what it is. It's the Alcock-Paczynski, or the anisotropy measurement, is a little bit high. It's about 2 and a bit sigma off from where you might expect it in a flat lambda CDM model. But that's what the data is telling us.
Is this what's driving the stuff you showed earlier about W?
It is an important contributing factor to that. Yes. One thing in this plot, I've removed some data points which come from Andreu's Lyman alpha talk. So just because I wanted to let him talk about those, I've just removed data points in these red circled areas. Okay, so that's actually the end of the galaxy BAO stuff. So now we can move directly on to Lyman alpha.
Thank you very much. So we have seen this plot earlier today in the beginning of the chat, and I'm showing it again to highlight that we have to use this extra tracer called the Lyman alpha forest, because it's the only way we have nowadays to measure the expansion at redshifts above 1.5 or so. So let me use this animation to tell you about the Lyman alpha forest. So this is a phenomenon that we see in high redshift quasar spectra. And I'm using this animation from Andreu. So you can see a simulated quasar spectra as it escapes from the host galaxy. And as the light travels across the universe, first of all, well, it's redshifted, but also every time that it encounters a little bit of neutral hydrogen along the way from the galaxy to us, there's some absorption features that appear. And what is interesting is that we can use the strength of these absorption features to reconstruct how much density, how much neutral hydrogen was there in each particular path along the way. Right? At each particular point along the way from the quasar towards us, we now have information about density in that point. So it's a different tracer of the fluctuations in the matter density. We're going to be using fluctuations in the transmitted flux. So here we're looking at the distribution, first of all, of quasars above redshift 2, both in orange for the Desi DR1 data release, and just comparing it to the SDSS DR16. This is the state of the art until today. You can see it in green. And you can see that we basically have a factor of 2 more quasars in this redshift range as well. And in blue, we are showing the number of Lyman alpha pixels divided by 200, because there's a lot of pixels in this Desi spectra, a lot of those pixels. And I'm showing this to show that basically there's the fairly wide redshift range. Most of the information, though, it's contained between redshift 2 and 3. And in this particular data release, we decided to just compile all this information into one single redshift bin of 2.33. We might revisit this for the year 3 analysis. We might use 2 or 3 redshift bins. We saw it in the Lyman ray, in the luminous red galaxies, that they were split into 3 redshift bins. We might do the same in the next data release. But all in all, it's 420,000 quasar spectra that we use for the Lyman alpha forest, and that's twice as many as SDSS over 20 years.
Why can you combine everything into one redshift bin? Surely what's happening at redshift 3 is quite different to what's happening at redshift 2.0. And
when you look at units of redshift, that looks like a very large jump, right? If you look, for instance, in units of light, like in units of years, it's not that much. There's more time. I think the Bright Galaxy Survey bin has a wider range in billions of years than the Lyman alpha bin. But yes, the universe evolves quite a lot between redshift 3 and redshift 2. And if we were to get information that was not just linear scales, it would be very important to look at very different redshift bins. And that, for instance, I know that there have been other talks in cosmology talks that talk about the Lyman alpha forest on small scales. There, it's very important to have very thin redshift bins. But BAO is a fairly linear feature, and we know that the evolution of the linear fluctuations is, it doesn't change. With redshift, it just changes the amplitude. So, we can model the amplitude of this wide redshift range just as an effective bias and report the BAO constraints at an effective redshift. So if we chose a fiducial cosmology that was very wrong, we would be washing out some of the BAO information. So we have also in an appendix of one of the supporting papers a plot that shows that, some of the information of BAO is washed out if you use a very wrong fiducial cosmology. But even then, the best fit result would not be actually biased significantly. On the left, you see what is probably our flagship measurement using the Lyman alpha forest data set. It was definitely the first one that was measured historically. We call it the Lyman alpha autocorrelation. And in that case, what we try to do is we correlate the absorption in 2 different quasar spectra. So we have 2 nearby quasars, each of them with a beautiful spectrum with hundreds of pixels with Lyman alpha forest information. And we correlate the absorption in those 2 pixels as a function of angular separation and as a function of line of sight separation. We can then combine these into another angular average correlation similar to the monopoles that Sesh was showing earlier. And you can see here on the left that we detect also a very clear BAO peak at around 100 megaparsecs divided by h. On the right-hand side, we show an alternative analysis that we can do from the same data set that is actually as powerful as the other one. We have only been using this for the last 10 years or so. We call this the Lyman alpha quasar cross correlation. And what we do here is we correlate the absorption in a particular pixel in one spectrum. We correlate it with the density of quasars around that. So we do that as a function of line of sight separation and transverse separation as well. And we can also compute the angular average or the monopole. What is interesting here in the bottom right is that the BAO peak is no longer a peak, it's a BAO trough. Right? So it goes down at 100 megaparsecs. There's nothing really strange there. It's just that one of the tracers has a bias that is positive and one of the tracers, in particular the Lyman alpha forest, has a negative bias. That might sound strange to some people that have been working with galaxies for years, but it's not that surprising. Whenever you have more density in the universe, you have more absorption, and that means that you have less flux. We have our cosmological variable as the fraction of transmitted flux. So in that case, it's a negatively biased tracer. You don't see it in the autocorrelation in the left, because you take that bias and you square it. But when you look at the cross correlation, you have to change a little bit your mindset. But the same basic linear theory works perfectly fine. You just need to use a different bias for the two tracers. We used a slightly different blinding strategy, but we also had a very detailed and complex list of validation tests that we had to pass before we were allowed to unblind. The reason why we used a slightly different blinding strategy is because, if you work on galaxy clustering, all you need to have is, as Sesh mentioned, Ra, DEC, and Redshift, and that's it. But we have to look at the spectra. We have to fit the continua. We have to look at, almost one by one the spectra. And if you shifted the positions of the pixels, we would have noticed, because there are very clear skylines that we know where they are. So if you mess around with the wavelengths, I would be able to unblind, by eye very easily. So we had to do something a little bit more complex. But at the end, it's just another blinding strategy that I think was very successful. So we did three types of tests. The first one is validations with synthetic datasets or mocks. We had 150 mocks that look very close to what the Desi DR1 dataset looks like. And we use those to validate that we can recover unbiased BAO parameters, but also we use them to check that we can estimate the statistical uncertainties very accurately. Then we had data splits. So we took our data, blinded measurements, and we split it into the autocorrelation versus the cross-correlation, what you see in different rest frame wavelengths of the quasars, what you see in the northern part of the data or the southern, the BAO constraints from high and low signal-to-noise quasar spectra. We tried also to split the quasar spectra in different types of quasars, for instance, by looking at the equivalent width of the carbon-4 emission. All of those tests, we passed them. And finally, we had this test that we call the robustness test, where we redid the analysis, still on blinded measurements, but doing slight variations in the analysis setup. So I'm going to show one slide going through some of them next. So what you see here are shifts in alpha parallel and in alpha perpendicular compared to the 1 sigma uncertainty in red. Those are the red vertical lines. And in gray, it's 1/3 of that 1 sigma uncertainty. And our requirement was that all these variations should not move the position of the peak by more than 1/3. And on the top left, in purple, we are seeing changes in how we extract these Lyman alpha fluctuations from the raw spectra. And on the right, in green, you see variations in how we measure correlations or how we estimate the covariance matrix. In orange, it changes in the fitting range. So whether we use more or less small scales or large scales, of course, always including the BAO peak around 80 to 120 megaparsecs or so. In blue, variations in the modeling, not only of the cosmological part, but also more importantly of some of the nuisances that we have to deal with, like redshift errors and things like this. And the only one that we highlighted a little bit separately, that because they had different requirements, are the variations in red. The variations in red are variations where we actually changed the data set. So we changed the rest frame wavelength range, we changed the observed wavelength range, the redshift range of the quasars, we mask some of the data. So we know that when we do that, there are going to be statistical fluctuations because you're removing some of the data. And in that case, what we asked for before unblinding is that we were able to explain any small shift by just statistical fluctuations. And we did that. So we were then able to unblind. And that was a very exciting day. That was December 8th, 2023. And we got together via Zoom. And this was the starting point. So we had these two parameters that Sesh already mentioned, BAO along the line of sight and transverse. This dashed gray cross centered at 1 is the fiducial cosmology that is based on Planck 2018, flat lambda CDM. We knew in blue the latest results from the SDSS collaboration. That was the state of the art until today. And then what we had then was the blinded measurement of Lyman alpha BAO. You can see it in dashed red. And it was an interesting result. We were all very looking forward to what would happen after unblinding because it was significant in tension with Planck. So we did the unblinding, and that's what we found. So a little bit boring, but we actually had a very extreme blinding in the transverse direction, almost as extreme as our blinding strategy allowed us. But I think it was good. We we went all the way, we fixed our methodology, even though the blinded result was kind of crazy, but that didn't bother us. We were confident about the results, so that's what we did.
That shows courage, staring down the barrel of the gun and saying, pull the trigger.
I mean, it was a little bit scary, if the blinding had been to the other direction, we would be, like claiming a Nobel Prize or quitting our careers. So what you see here is that, these results from Lyman alpha BAO in Desi DR1, they're both consistent with Planck lambda CDM, and also with the previous measurements from SDSS DR16. There's a kind of like 10% correlation between those two measurements, between red and blue ellipses here. Okay, so then what I'm showing here is these red ellipses that we saw before. I'm splitting them now into the measurement from the autocorrelation in blue and the measurement from the cross correlation in black. And it was really great to see that they are super consistent. We knew that before unblinding, right? We had done this check, but we can see it also in this plot. They align very well even after unblinding, and the combined constraints in red are a lot more powerful because of this combination. I'm also showing here in this dashed red cross the parameters that Sesh was mentioning before. So we have a roughly 4% measurement of the Alko-Paczynski parameter at this redshift of 2.33, and a 1.1% of our most accurate distance of BAO from this isotropic scaling. That is a slightly different definition than the one used by Sesh, but that's a technicality. So it's a 1.1% measurement of BAO at redshift 2.33. So in case you're interested in the details, the main publication presenting the final results, it's Desi 2024-4. This was a project that we have been leading for the last few years with Alma González Morales at the University of Guanajuato and Julian Key at Berkeley Lab. And it has also today 2 more papers on the archive and on the Desi website. One is led by Andreu, a postdoc at Ohio State University, and it has all the validation analysis using mock data. And then Julian Key at Berkeley Lab has another supporting paper showing the characterization of contaminants in the autocorrelation. And in the last few years, using this early data release of Desi that we heard about earlier today, we had also a bunch of other papers that were very useful for these results that we present today. Some of them, for instance, are listed here. Cesar Ramirez Perez, PhD student at TIFI, led this analysis of the curation of the Lyman alpha dataset. Callum Gordon, also PhD student at TIFI, presented the 3D Lyman alpha correlations from the early data. Abby Bolt, a PhD student at UC Irvine, had a study of the redshift errors and the impact of those redshift errors in the Lyman alpha quasar cross correlation. And finally, Hiram Herrera Alcántar, a PhD student at the University of Guanajuato, presented the publication describing how we construct these synthetic Lyman alpha datasets for Desi. So I'm going to let Sesh now tell you about probably what is the most exciting part of this talk, and it's the cosmological constraints from Desi BAO.
Just before we go to cosmological constraints, something maybe, Andreu's been working on Lyman alpha for a long, long time, and there's a lot of technical details that he covered here. But for me, as a person who got into working with Andreu just a few years ago, there's something really, really cool about the Lyman alpha forest, right? I mean, these quasars, they're supermassive black holes at the centers of these galaxies billions of light years away, and they are shining so brightly, and they're basically illuminating matter between us and the quasar. They're acting like a backlight. I mean, that's an amazing...
We are cross-correlating the shadows.
Yeah, exactly.
Of the clouds of gas.
The one analogy that I've used to try to describe this to people is, you're in a dark theater and there's a bright spotlight that illuminates the little grains of dust in the air along the way, and you're measuring the positions of those grains of dust. It's a super cool measurement. Okay, so cosmology. This is maybe what a lot of your viewers have been waiting for. Right, so let's start with just plain flat lambda CDM and what BAO measures in that model context. And actually, what BAO does is if you restrict to just flat lambda CDM, it measures 2 parameters. One of them is the matter density, omega matter, and the other one is this combination of the Hubble constant, H0, and the sound horizon, RD. So we can't measure either of those 2 individually using just BAO, but we measure omega matter and H0 RD. And this plot is showing you the constraints that you get in this parameter space from each of the different redshift bins that we've discussed so far. So, well, actually, the LRG redshift bins, I've combined 2 of them in this plot just for convenience. But what you can see is two of the measurements from the bright galaxy sample and from the quasars, where we didn't have enough signal to noise, and I said we only measured one scaling parameter instead of two. There you get these unbounded contours. But for everything else, you've got a nice like ellipse or a bounded contour in this space, and the orientation of these contours changes as you go from low to high redshift, and they all overlap. And so the real power of Desi is that you're able to make these measurements at multiple different redshifts and then combine them all together to get this small little black contour that's overplotted on top of everything else. And really, you could talk about this plot for ages. There's a lot of physics in here about how BAO is actually measuring things. But yeah, it's a nice, cool way to start off understanding what we're able to do.
But the very short story about why it's these two data points is essentially that the H0 RD is actually setting the distance that the BAO is today, and omega matter in flat lambda CDM is telling you how that evolves with redshift.
Yeah, exactly. So omega matter controls the shape of the Hubble diagram plot that I showed earlier, and H0 RD is like a normalization factor. Right. So just to zoom in on the little black contour from this plot and show it in a different color on this one. And so here we have the Desi BAO measurement again in omega matter and H0 RD compared to SDSS, the previous result. And we have a sort of way of combining the Desi results and the SDSS results to get a sort of best BAO data set, and that's shown in green. But mostly in the rest of this talk, I'll be concentrating on Desi alone. And you can compare this to the CMB, where the CMB is here is a shorthand for Planck temperature and polarization, plus a combination of Planck and ACT DR6 CMB lensing results. And the end result is that Desi BAO measurements are consistent with the CMB. They have a slightly larger value of H0 RD, but it's not in any significant tension with the CMB.
And why is Desi BAO not much better at this particular constraint than SDSS?
This is because Desi is measuring the BAO much more precisely than SDSS at high redshifts, where SDSS wasn't quite so great. But at low redshifts, because in the plot that we showed earlier on, the Desi footprint is currently still pretty small. So at low redshifts, we just haven't yet got the same effective volume as SDSS had. And when you do cosmology constraints like this, low redshift BAO measurements actually count for a bit more than high redshift BAO measurements. And so you average all of these things out, and Desi is doing a little bit better than SDSS on those combined cosmology constraints, but not a huge factor better. This will change. Even with the next data release, it'll be significantly better than SDSS. That was just what you can measure with Desi BAO alone. And as Andreu was mentioning, if you use some external data to calibrate your sound horizon expectation, then you can break the degeneracy between H0 and the sound horizon. And then you can get constraints in omega matter and H0. So there's different kinds of external data that you could calibrate your sound horizon with. One of them is just Big Bang nuclear synthesis. It's a very standard type of measurement that we do for BAO. So you have a Big Bang nuclear synthesis measurement of primordial element abundances that you can use to convert, using all this complicated early universe physics, into a baryon density. And if we know the physical baryon density, we can use that to calibrate the sound horizon. And so that's sufficient to break this degeneracy. And that contour is shown here in blue. What we can also do is to combine that BBN prior with a prior on the acoustic angular scale from the CMB. So the CMB measures many things, but the single parameter that it measures most precisely and most robustly is this acoustic angular scale. It's probably the single best measured parameter in all of cosmology, and it's incredibly robust. And essentially what it is it's a BAO measurement. It's exactly the same kind of BAO measurement that we're doing at low redshifts, but it's done at a redshift of 1,100. And so I consider this a very, very robust piece of external information that we can add in. And if we add that theta star, the acoustic angular scale, as a very conservative prior, plus BBN, plus BAO, we get that orange contour. So you get a very precise measurement of both omega matter and H naught.
I think you kind of said what I'm about to say, but maybe you didn't say it quite as explicitly as I'm going to say it. But you used the word robust. I think robust is the key thing here, that this measurement of theta star is robust. And because there's these things like this A lens issue in the CMB that might be happening at small scale lensing.
Exactly. If you had some potential systematics, I mean, people have wondered about, maybe some systematics at high L in the CMB power spectrum and so on. Theta star really doesn't care about those things. Theta star is incredibly well measured just using the low L multiples of the CMB. So it is very robust for exactly the kinds of reasons that you're mentioning. It doesn't depend on this A lens parameter or any controversies about that.
Whereas that other stuff might push the overall CMB contours because it does measure omega matter because there'd be more lensing or less lensing or whatever.
Potentially, yes. Okay, so also on this plot, slightly less interesting than those two contours, I think, is if you just directly take the CMB measured value of RD and calibrate straight off that. It's probably less robust than the other two things, and it doesn't give particularly any better constraints or anything. But all of these things are mutually consistent, and they all prefer a slightly higher value of H naught than the CMB. But we quantified, how much these things might disagree with each other, and it's not significant. So I would say that we've got a consistent picture from BAO and external priors as you have from the CMB. So, and if you just put that all together, we can then put this on this figure. There are various different ways that we can measure H naught. So in the bold blue lines are Desi BAO plus different combinations of external priors. And you can see that they all lie slightly higher than the orange ones from the CMB, but consistent with it. And all of them are lower than Shu's Supernovae plus Cepheids, which is right at the bottom in green, local distance ladder measurement. So we've also on this plot included, how the constraints change if you, instead of using Desi BAO alone, you had Desi plus SDSS. But again, I won't go into that just for the purposes of this talk. And so you can put these all together and combine Desi with the CMB, which isn't done on this plot, but you get a number which is shown at the bottom left, H naught 67.97 plus or minus 0.38 kilometers per second per megaparsec. And in terms of the Hubble tension, this clearly shows that we're still in tension with local distance ladder measurements from Shu's. And here's just a way of quantifying what that tension is. But so far, I've only talked about flat lambda CDM. When you change the background, then all of these results change a little bit. And although BAO always favors low values of H naught, once you change the background cosmology model, then the error bars increase. So the level of tension with the Shu's direct measurement can jump about a bit as well.
Although it is still interesting here that with W naught and WA and omega K, the Desi BAO plus CMB is still in 3 sigma tension. I mean, 3 sigma tension is not that big, but there's a lot of free parameters there that could have completely removed the tension.
Yeah, there's a lot of free parameters.
And if you added supernovae, it would be even stronger.
So yeah, even though you guys are seeing evidence for W naught and WA not being their standard values, that's obviously not like linked to the Hubble tension.
It doesn't help with the Hubble tension. No, in fact, it almost goes in the opposite direction in that the central H naught value gets lower. The tension decreases formally because the error bars get a bit larger, but it's not pulling you to higher H naught in any way. That's all just basic lambda CDM. One very interesting thing that we can do with BAO is to tighten the upper limit on the neutrino mass and the sum of the neutrino masses. So I've got a slide here that sort of indicates why this is happening. So this is just CMB only, or CMB without lensing and with lensing. And it's showing you sigma m nu versus H naught. And there's a geometrical degeneracy here, which is as you decrease the value of H naught, you allow more neutrino masses. And that's just, it's an intrinsic thing to the CMB. You can have more, a higher neutrino mass, but compensate that by changing the value of H naught. But what Desi BAO is able to do is to constrain the value of H naught and break that geometrical degeneracy at low redshifts, and therefore limit the neutrino mass upper bound. So this plot shows you both the CMB plus Desi joint constraint, and just as the vertical band is to guide the eye, it's what H naught value Desi BAO would prefer when combined with the external priors that we just discussed. So that explains why the green contour is where it is.
So is omega BH squared here the BBN prior?
Yes. I mean, you could have an omega BH squared from BBN, or you could say, well, the CMB is going to give you a constraint on omega BH squared. Either way, you'd get very, very similar constraints here. So what this does is it places us an upper limit, a 95% upper limit on the sum of neutrino masses at 72 MeV, which is a fairly large improvement, or a reduction in the upper bound compared to the previous best values in the literature. The important thing to note is I mentioned how H naught was slightly larger with Desi, and really that central value of H naught has quite an important role to play here. Even though the precision with which we can make BAO measurements has only improved a small amount, because the central value has shifted to slightly larger H naught values, that is really driving this improvement in the neutrino mass constraint. But it's really important to mention, which sometimes gets lost in other talks, is that firstly, this limit is very strongly dependent on the background. So that limit of 72 MeV is purely coming from a flat lambda CDM background. If I allow for W0 WA dark energy evolution, then it blows up. Then your limit is at nearly 0.2 EV.
I think if W0 or WA ended up being different from -1 and 0, people would take that and wouldn't mind too much about the weakening neutrino mass constraints.
Exactly. That's a point that I totally agree with, and I've said it many times myself. But the other thing to bear in mind is that it's not just background dependent, it also depends on the priors that you place. So in our main analysis, we've allowed the neutrino mass to go all the way down to 0. So our prior is basically just sum of the neutrino masses must be greater than 0 eV. It's a non-negativity bound. But based on terrestrial experiments, you could place more physical constraints on this. We know what the physical lower limit is, and if you change that prior, then you will shift the upper limit that you get. I think the value that is given with a prior at 0 is still meaningful, because it's a direct comparison to previous results in the literature, and you can always deduce from that, using a Bayesian evidence approach or something, what this really means for the neutrino mass hierarchy, whether the normal hierarchy is favored or how much it's favored over the inverted hierarchy.
The lower limit from terrestrial experiments is 0.06 EV, right? So this is 0.07 and 0.06 are almost the same number. And I know you say it's prior dependent. Yeah, if you set a prior that it cannot be less than 0.06, you're going to find that it is bigger than 0.06. But that doesn't feel that interesting a statement, right? Like, this is saying that almost all of the volume of the preferred data space is less than 0.06 EV. That seems like quite a...
The other thing to bear in mind is that if you look at, say, the best chi-squared, the best fit chi-squared, or the maximum likelihood point with your prior that allows it to go below 0.06 EV, and compare it to what it is at 0.06 EV, the difference is not really big. It's not quite a 2 sigma level of so you're not ruling out the physical neutrino mass at any great significance from cosmology. And I think that's perfectly consistent with it just being a statistical fluctuation that will sort itself out when we get more precise data, when we actually make a neutrino mass measurement instead of placing upper bounds.
Or like maybe by the end of Desi, this 95% bound becomes something like 0.04. And at that point, then you say, well, there's something really interesting, because, like, it might point us to like something new in the neutrino sector that, like neutrinos might behave in a non-standard way such that they don't impact cosmology in the way we thought they were going to impact. And that itself would be a very interesting result.
Yeah.
But we're not there. We are not at that point.
Or it could be that we have dark energy evolving with time, and
There
then
you
all
go.
bets are off.
Or something else that is mimicking dark energy evolving with time, I suppose, as well. Like a W naught and WA are just like ad hoc parameterizations, and them being statistically significantly different is huge, but doesn't necessarily mean that they're the right parameterization, obviously. Yeah, I don't know. There's still, even only being the best fit chi-squared below 0.06 compared to the chi-squared at 0.06 only being 2 sigma different. I don't know. It's starting to be like a little voice in the back of the head of like something interesting might be starting to occur. And maybe, as you said a number of times, it's W being different. Who knows? Yeah, this is exciting.
So let me also make another point that remember that here we're only talking about the BAO results from Desi tier 1. The neutrino mass in particular will be, the constraints will be also more interesting when we look also at the full shape of the redshift space distortions data from Desi tier 1, because the growth of structure is also affected by the neutrino masses. So I think we don't have to wait for year 3. Just with the full shape analysis of galaxy clustering from Desi tier 1, we will learn more about neutrino masses.
Now we just move to the big one, the one that we teased you with at the start of the video, dark energy.
Turns out to be the well-named telescope.
Yeah, well, exactly. I mean, we are the Dark Energy Spectroscopic Instrument. Right, so the constraints I'm going to show you here are for a model with a time-varying equation of state parameter. So there's the standard W0 WA parameterization, also called the CPL parameterization. And we do have results in the paper for a fixed WCDM model where the equation of state doesn't vary with time, but I won't cover that in these slides.
Why are you not preferring that one? That's like the kind of, first step.
Yeah.
There might be something to be said from a physics point of view. I'm not the expert there, but my understanding is that some physically motivated models for how W would change with time, if you just try to get one number, it might look like W is still -1, because you're just, you're hiding the fact that it has changed, and it might have crossed -1, but averaged to -1. So I don't know. Some people have very strong opinions there. I like plotting both in my papers.
In fact, what I'm going to show you here is that we have some sort of hints, some evidence of a time-varying equation of state. But if you look in the paper, where we look at a purely WCDM model, we're very, very consistent with the constant W being equal to -1. Right, so that's the introduction of the model. Let's start by just putting Desi BAO alone. And these contours are really quite large. This model has too many free parameters and too much freedom in the expansion history for BAO alone to be able to say anything particularly statistically significant about it. But you do see that BAO are somewhat favoring W0 that is greater than -1 and WA that's less than 0. But now let me add in CMB. So BAO plus CMB, and again, these contours are not, they're bounded by our prior at the lower edge, but you can see that up near the top, the 2 sigma 95% contours don't include the lambda CDM point in the crosshairs. It's not a very high statistical significance at which lambda CDM is rejected here. It's about 2.6 sigma from just BAO plus CMB alone, which we wouldn't want to claim too much for. We can then start to add in supernovae datasets. And what's interesting here is that there are 3 current supernovae compilations. So the oldest one is a Pantheon Plus, Skolnick et al. 2022. And this is a compilation of, I think, something like 1,600 supernovae. It comes from, many different telescopes, and they've taken a lot of care about reducing the systematic errors and so on. But if we put this in, it's consistent with the previous 2 contours. It's also reasonably consistent with lambda CDM. This is just Desi BAO plus the supernovae, no CMB in here. If we take a newer data set that uses most of the same actual physical supernovae as Pantheon Plus, but has a totally new data reduction technique and a hierarchical Bayesian modeling for this. Then we get this orange contour. This is starting to, just Desi plus union 3, starting to pull away from lambda CDM a little bit. And then a very recent dark energy survey 5-year supernova program result from Davis et al. And that's in green, and that kind of overlaps nicely with union. Again, not so good with lambda CDM. But one of the points I want to make here is that this was just combining 2 different probes at a time. And really, to get the full statistical significance, we want to have BAO and CMB and supernovae. But the point of breaking it down is to say that each of these individually, or in 2x2 combinations, all somewhat favor that quadrant of this plot where W0 is larger than -1 and WA is less than 0.
I guess you didn't show just CMB and just supernovae.
The reason I didn't is because Desi is a BAO experiment, but you can find those plots in the supernova papers that were referenced on this slide. And they all have very similar conclusions. Okay, so let's actually put all 3 of them together, and then this is the plot that we get. So there are 3 different supernova data sets, and when we combine them with Desi BAO and CMB, the results are all consistent with each other in that the contours all overlap, but they do give somewhat different estimates of the uncertainties. And consequently, the 3 different combinations give you a different statistical significance for rejecting lambda CDM. So Desi plus CMB plus Pantheon plus is 2.5 sigma away, plus Union 3 is 3.5 sigma away, plus the Dark Energy Survey supernovae is 3.9 sigma away. Now, I'm quoting these numbers in terms of sigma. That's, obviously, it's just a simple, easy way to encapsulate it for the talk. We do base factors and other calculation metrics. Those are all included in the paper. But the picture is always consistent, which is that there's hints of evidence for what I'm going to call, in quotes, thawing dark energy. So dark energy that was, the equation of state was more negative in the past. And how much you want to interpret these things really depends a little bit on which supernova dataset you like, and also how much you weight 2.5 sigma up to 3.9 sigma. But there's weak to moderate evidence in terms of base factors for all of these for an evolving dark energy equation of state versus lambda CDM.
There are 2 questions that leap out at me at this point. One of them is kind of how much is this driven by the supernovae? Because I know this Desi 5 paper did make similar claims. I guess they didn't have 3.9 sigma, so some of it's driven by the BAO. And related to that first question, how is the physics going on here that they're like different, they're sensitive to different things? What is the supernova adding to BAO? What is the BAO adding to supernova to better constrain these 2 W parameters? Like, I know you said that you're a BAO experiment, but I would have loved to have seen plotted on the top what the supernova contours actually look like to see how this degeneracy is.
Well, so the supernova plus CMB contours are presented in their papers, so that's an easy plot to find. Although I think in most of their papers they also use older versions of BAO from SDSS because they are really complementary. One of the things that helps, I believe, is that, well, you remember, like, the BAO can also measure the Hubble expansion at the different redshifts, right? BAO, while supernovae is just an integrated, right? It's a distance, so it's an integral of 1 divided by the Hubble expansion. So in that sense, BAO is really unique in that. On the other hand, BAO, it gets a little bit tricky to do a good measurement at low redshift because you just don't have the volume. You are quickly dominated by cosmic variance at the very low redshift then. While supernovae, it's fairly easy to find supernovae at low redshift. They're easy to, they're brighter. So I think supernovae help a lot at low redshift, and BAO brings this qualitatively different information by measuring h of z, even at redshift 2.
So one of the things, your very first question about which one is contributing, one of the things I was trying to bring out from the earlier slide I showed is that all 3 of these probes are contributing a bit to pushing this result to where it is. And if you take CMB plus supernovae by themselves, you don't get a very significant result. If you take BAO plus supernovae, it's consistent, but it's not statistically as significant. And if you take BAO plus CMB, it's the same sort of picture. So they're all consistent with each other. You really need all three of them together to be able to, reach the statistical significances that we've quoted here.
So it's not even necessarily that they have different degeneracy directions, blah, blah, blah. It could just be that they're all kind of blobs in this bottom right-hand quadrant. And when you put three blobs together, the statistical significance increases.
Yes.
Yeah, the degeneracies in those plots that Sesh showed in the earlier slides, they look a little bit different, but not that different. So I think here it's just a matter of adding more data. I'm not sure. Yeah. It might be that the degeneracies in other parameters are different. We are just looking at two of the parameters that we vary. So it might be that we are breaking the degeneracies in other dimensions. I'm actually not sure.
So from the BAO perspective, if I were to single out a single redshift bin measurement that is contributing the most to driving the BAO results to where they are, it would be the lowest redshift LRG bin with the ratio of DM to DH, so that measurement of the anisotropy that you picked up on in one of the earlier slides. But it's not just that bin, it's a combination of everything and all measurements together.
The very next slide you showed after that one actually showed that there were 2 or 3 data points that were kind of below the lambda CDM.
Yes, exactly. So just in the isotropic measurement, there's quite a few points that are below where Planck is. So that also contributes. It's a combination of all of these things. But what supernovae are really helping with is constraining things at redshifts below 0.5, where the BAO measurements currently don't have that statistical power.
So the other thing that leaps out to me about this plot, something that seems just really mysterious if this is new physics, is that if I did continue this up to WA equals 0, it happens at -1. W naught equals -1. And if this was new physics, that would seem like a weird coincidence.
Yeah. There's another thing you could do. So, you can find a different parameterization, for instance, by choosing some pivot redshift that we measure best. And then, these ellipses that look very elongated in this direction would look less elongated in that other direction. So we had some chats about this. And in that case, you'd still have the same amount of tension with lambda CDM, but you wouldn't see these bananas. I don't know if you would feel more comfortable with that plot.
Maybe, but it does go back to what Sesh actually said as a true statement, that if you just consider the W naught model with WA fixed to 0, you do hone in on W naught equals -1, and that's not a by eye kind of effect. That's the actual statement about the data.
So maybe to rephrase what the kind of question that you're asking, Sean, is, this W naught WA model is a bit of a toy model. It's a parameterization. If we actually had a scalar field dark energy that was causing this time evolution, could we find a physically justified model that matched these central values for W naught WA that we find? And I think that is a really interesting question. It's a question that is outside the scope of this Desi paper, but I do know that there are some papers in the works that will try to address this.
It does still then seem like a weird coincidence, though, that if this scalar field model is correct, it looks like W naught equals -1 when you treat it, parameterize it as just a W naught value.
So, Sean, maybe you could look at it in a different way, right? If the average W over time, or if you parameterize it with just one W, was far from -1, we would have seen it before.
I wanted to put up a little summary of what we've done, where we are at the moment. So we have the most precise BAO measurements ever made, and that's presented in this paper. Cosmological results, we've got an approximately 1% precision on H0 from Desi BAO plus some external priors like BBN. Within flat lambda CDM, we're consistent with the CMB. We have neutrino mass constraints. There's a whole bunch of things on spatial curvature and so on that we didn't discuss in this talk, but please look at the paper because there's spent a lot of time writing stuff that we think will be really interesting. And then the most sort of intriguing thing at the moment is these hints of time-varying dark energy equation of state. And then we've got a link. That's where all the papers are out today. And then we should look at the future, right? What's to come? So we've talked quite a lot during this about the full shape analysis, the full power spectrum constraints, which include redshift space distortions and so on. And that analysis is going to come soon. So that's a matter of a small number of months, hopefully. But as we also mentioned in this talk, we've now already finalized the the 3-year data set. So that data acquisition is completed, and that will then come out as data release 2. And that is on a somewhat longer time scale, but some of the most exciting parts of that may be accelerated given the results that we've already seen. And then by the end of the survey data collection will finish in 2026. But by the end of that, the full Desi dataset will be about 3 times larger than what we currently have. So we're going to have a lot more constraining power. And those analyses will be the really the most exciting things to look forward to. After 2026, we're going to transition on to a new survey called Desi 2, which looks at different redshift ranges and different kinds of targets. So that's something to keep an eye out on as well. That'll be very interesting in the future.
There's also something that we haven't mentioned in this final slide because it's not up to us to do, but the supernova community keeps working on more analysis. The CMB, there are also ongoing CMB surveys that will also have results soon. So maybe before the Desi year 3 analysis are out, one of the other collaborations will present updated results that will also change this picture.
Yeah, so I mean, related to that, in these contours, at the moment, for each of these, I mean, for the 3 different supernova datasets, the results are mutually consistent. But you can imagine that as the errors shrink here, if the central values don't move around, then there might be a time when they're not mutually consistent. So hopefully one of the things that will come out in the next few years is a convergence within the supernova literature as well. And we'll be doing our best to on the BAO side to really tighten those constraints. But I think it's a joint cosmology effort from all sides.
And if there's systematics in Desi BAO, it will also be interesting to look for Euclid BAO, right? In a couple of years or so, we should be hopefully having the first Euclid results. They will not be competitive, I think, in 2 years, maybe in 3-4 years, we'll have competitive results. So that's also going to be interesting, especially if it goes in the same direction.
Oh, wow. So yeah, that's a lot to digest, and very interesting results on Dark Energy there. So thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this to you, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, check out this talk by the ACT Cosmology group on their lensing result from midway through last year, which I think was hiding there in the CMB constraints that Sesh and Andreu were showing today. And thanks, Sesh and Andreu, for the great talk.
Thank you. Bye-bye.